In the last few videos, we've been working on both Faraday's law and Lenz's law. So let's see if we can bring some of those ideas together here. So we've got 140 loops of wire with an area of 0.072 meters squared in a magnetic field of 0.85 Teslas. And what we're going to do is we are going to decrease the magnetic field to let's go with 0.50 Teslas. We're going to decrease the magnetic field to 0.5 Teslas let's go with 0.62 seconds. Okay, so what we're going to do is we're going to find out what is the induced EMF, and we are going to draw the induced current for the loop. Okay, let's just start with the induced EMF type stuff, the flux ideas and that type of stuff, and then we can build in the induced current type stuff afterwards. Okay, so we can find our fluxes. You guys have done this type of thing before. So I'm going to find my initial magnetic flux, BA cos theta. Of course, the first flux here, cos theta is going to be equal to 1. That's no problem because, of course, the angle between the normal and the field is 9 degrees or 0 degrees, and the cos of 0 is 1. Also, you can look at it. It is set for maximum flux, so cos theta is going to be equal to 1. So if we do B times A, we got that 0.85 times 0.072. We've got about 0.0612 Webers of flux going through it. Then the magnetic field is going to get weaker, so we will have our new flux. So that'll be our same type of calculation, except of course it should be weaker this time. So we'll just do the same type of thing. So we got the B of 0.5, and we multiply that by the area of 0.072, and we will get our 0.036 Webers there. Okay, so we got our first flux, we got our second flux. So of course we want to know our change in flux. So we'll just subtract the two, and it'll end up being negative because we are having less flux. So the change in flux is negative 0.0252 Webers. Okay, so now to find the induced EMF, we can go to the expression that we've used before. Induced EMF is equal to negative, we use a fraction, right? N, change in magnetic flux over change in time. Oops, got an extra divide in there. Okay, all right, something like that. So we got the N value, that's our 140. We just found our change in flux, and of course our delta T is up there. And the nice thing is our negatives are going to cancel out. So that makes it a little bit easier. And then we just sort of piece everything together. And if we do that, we should get an induced voltage of around 5.7 volts. Okay, so there's your basic induced EMF calculations. Now let's see if we can find the induced current. Okay, so if I look sort of like the way we did before in the sheets, the magnetic field inside the loop was going that way. It was going towards the right, and it got weaker. So the coil has less magnetic field going this way, going to the right. So if the coil is getting less field to the right, it is going to make field to the right to try and compensate. So the induced magnetic field would be going in the exact same direction. So there's my induced magnetic field. It would also be going towards the right. And then if I use my good old right-hand rule from grade 11 as well as grade 12, if I do my right-hand rule for the current, I like to reverse the general functions for coil stuff that. So I'm going to point my thumb to the right, and if I look at the way my other fingers are looping around in the shape of the current in the coil, my fingers are generally coming around this way, and then the current would be going back up this way. So that would be the direction of the induced current. And of course, this is for the magnetic field getting weaker. If the magnetic field was getting stronger, it'd be the exact opposite. The induced current would go the opposite way, the induced magnetic field would go the opposite way. It would all be opposite. Okay, so there's a little combination of the two things put together. Okay, so let's try another one. Okay, so in this question, it's sort of like a similar idea. We got the coil in there. We got 85 loops with 0.165 meters squared. It's in a 2.8 Tesla field. and it's sort of like an angle. It's like 40 degrees off of the horizontal. And what we're going to do is we're going to make the coil horizontal in 0.75 seconds. Okay, and we're doing the same type of thing we did before. We're going to find the induced EMF, and we are going to draw the induced current in the coil. Same type of thing. Okay, so again, let's find the fluxes. Let's see what we can do. So first flux that I'm going to find. Let's see. So we're going to find the first flux. So BA cos theta. Okay, I've got the B, I've got the A. That's E. Now the cos theta, the angle. Which angle do we use? Do you use the 40 or do you use the 50? Well, again, you can do the geometry, that type of stuff. I like to think about maximizing, minimizing. If that coil is only 40 degrees off of the horizontal, it's closer to a maximum, or it's closer to more flux than it would be to less flux. So since it's closer to more flux than zero flux, I want to take the bigger value for cos 40 or cos 50, and cos 40 is bigger than cos 50. So I'm definitely going to be using the 40 degrees. And if you did your geometry and actually drew the normal off of this thing, you'd actually see that it is actually 40 degrees. All right, so we can punch those things out. So we've got the B value, there it is, B value of 2.8. We'll multiply that by our area of 0.165 and then times that by the cos of 40, and we get approximately 0.354 Webers. And then, of course, the coil is made horizontal. Okay, so the coil is made horizontal, so it goes flat. And we'll find our new one. Now, the cos theta, it's going to go flat. That's going to be maximum flux. It's like totally open up. So that's going to be equal to 1, so you don't even have to worry about that. So we just do the same thing with the B and the A and multiply the two together. And we should get 0.462 Webers. Okay, so now we've got to use these guys, and let's get our change in flux. So we got a positive change, got stronger. So we'll subtract the 0.354 from our new flux, and we've got 0.108 Webers is the change in flux. Okay, so now we can do the same type of thing we did before. We can find the induced EMF. So the induced EMF is going to be negative N change in flux divided by change in T. We've got the N value, we've got our change in flux, we've got our time. We just have to put them all together. And we do have a negative out in front, so this one will be negative. So we take care of all that, and we get around negative 8.43 volts. No, nope, sorry, that's wrong, that's wrong. Put the wrong number was sitting in my calculator display when we punched it all out. Okay, so let's try this again. We got the 85 loops, and we're going to times that by the 0.108. Okay, that's fine, and then we'll divide by that 0.75. Oh, it should be bigger, yeah. So we got around negative 12.2 volts. Okay, that's a little better. All right, so now let's get the induced current. Okay. So right now, when we started the whole thing, there is magnetic field going up that way through the coil. And when the coil goes flat, it's going to get more going up. So since it's getting more going up, it's going to make magnetic field going down to try and cancel out that change, try and counter it. So it's going to make field going down. So the induced magnetic field is going to be going down. And then again, using our good old right-hand rule, if this thing's going to have magnetic field going down, the induced current would be coming around this way, looping around, and then going around the back this way, then coming back in the front over here. So that's the way the induced current would look, something like that. Okay, so there we go. Okay, so there's another question, putting some of the Lenz and Faraday stuff together. And now it's time to start looking at one of the major applications for this that you guys actually use all the time. So to show you guys what you guys often use this induction stuff for, like pretty much every single day, we're going to go back to a diagram I showed you guys a while ago where I drew something like this. It's like a piece of iron. Well, that's just terrible. Let's try that again. It was a piece of iron. Here, I can use my circle tool even. There we go. Something like this. There we go. And then let's draw another one, something like that. Oh, that's a little better. Okay, so we had a piece of iron, and we can shade it in a little bit. Okay, so this is a piece of iron. And then what I drew is, I'll draw 1, 2, 3, 4, 5, 6 turns of wire here. And that would connect to a power supply or something like that. And I'm going to draw 1, 2, 3 blue wires on that side. There we go, something like that. Okay, so this should look familiar from when we did our basic induction type stuff. And basically on the first side here, this is where we have, we put in a current. And of course, here we have magnetic fields going through the iron. And on this side over here, of course, this is where we can actually create a current. And it wasn't just current. We also had EMF as well. And on this side, we had EMF as well. So something like this. Now, here's one of the kind of neat things about it. Over on the green side, we have, I drew 6 loops. Okay, so on that side, I had, so I'm like on the first side, okay, I had 6 loops making, so basically 6 magnetic fields. Okay, and of course, those magnetic fields come together and go through the iron. But on the second side, on over here, we only have 3 loops. So on the second side, we only have 3 loops. We only have 3 loops to actually use those magnetic fields. So we have the red side, or the green side with the red writing. On the first side, we've got 6 loops making 6 magnetic fields. We've got 3 loops on the right-hand side to use the magnetic fields. So even if I expand on this, each of these loops here has an EMF that goes with it. Over here, these loops over here have EMFs that go with it. Every single one of the loops. Now, since we've got different numbers of loops, we actually end up with different EMFs. And it's kind of cool when you start like playing with this and figuring this out. But on the left side, there's more voltage than the right side. There's more EMF. And it would be exactly twice as much because one side has twice as many coils. And because you change the number of coils that actually both either create the magnetic field or take advantage of the magnetic field, this actually can be used. What you can actually do is you can actually change the EMFs or the voltages based on the number of coils. So you can actually change the voltage. Okay, the number of coils sort of dictates how much you can actually use. In chemistry, you sort of probably call this like the limiting agent. And it sort of limits how much you can have. You got more, you got more, you got less, you got less. It sort of limits things a little bit. Now, this is what is called a transformer. Okay, and you guys may have heard of transformers aside from the robots before. And one of the top places that you guys use transformers actually looks something like this. And this is the inside of the little box plug-in transformer that's often used for charging phones and a lot of other electronics. A little box that plugs into all. Well, that's because it's a transformer. And there's a piece of iron that goes all the way around as well as right through these 2 coils. There's one coil there. There's one coil there. This coil has a whole bunch of little wires attached to the outlet, which is 120 volts. This one has fewer turns of wire attached to whatever you want to use it for. And you guys remember from basic circuits and that kind of stuff, a wall plug uses 120 volts. The ones your phones use, those guys are actually meant to use 12 volts. So one side's got 120 volts, the other side's got 12 volts, which means this side actually has 10 times more turns of wire than the other side. And transformers are used to change how much volts you have so you can do different things with them. So this is one of the top applications for induction that's used all the time, including charging your phones. And this is what we're going to look at a little bit in the next video.